In synthesis of ceria graphene, nanocomposite for cyclohexene epoxidation reaction. Here we are using a composite of graphene for the epoxidation reaction of cyclohexene, and the preparation of graphene and the composite is performed in a green method. We all know graphene is the single sheet of graphite, and it contains sp2 carbon and a high conductivity, and it can be transformed into other forms of carbon nanostructures, and the high surface area and electronic properties makes graphene suitable for versatile applications. And our specific application is in catalysis. And about graphene synthesis, it can be synthesized via both bottom-up as well as top-down methods. And the successful methods for the preparation of a perfect sp2 hybridized carbon-containing graphene is mainly via bottom-up methods such as CVD, epitaxial growth on carbides, and but the most economical way for the synthesis of graphene is via graphite oxide, and this will lead to the introduction of enormous functionalities to graphene, and further reduction will lead to the formation of graphene or reduced graphene oxide. For graphite exfoliation, this is a good way, and the functionalities can enhance the incorporation of foreign species such as metal oxides to graphene. But the problem is that we are getting a defective graphene with restricted electron mobility, limiting its electronic applications, as well as in catalytic applications where electron transfer is highly important. And the another problem of graphene oxide assisted method is that here graphene is prepared under drastic oxidizing conditions and in the presence of toxic or oxidizing agents such as sulfuric acid, KMnO4, and a lot. And instead, the most preferred method for graphene synthesis is via green methods. We all know that green methods or green synthesis adopts eco-friendly approach, and not toxic chemicals are not used there. And this method is already extended for the large-scale production of many nanoparticles, and including graphene. And here, we prefer the liquid phase exfoliation of graphite for the production of graphene. But usually, for liquid phase exfoliation of graphite, the toxic solvents such as NMP, N-methyl pyrrolidine, or DMF, dimethyl formamide, is used. And this is not a green technique. And also, the yield of graphene is low. So as to improve the yield of graphene, we can incorporate surfactants during preparation. And in addition, surfactants can enable the use of water as a solvent for graphite exfoliation. And in the present technique, we are using a surfactant P123, pluronic P123, which is polyethylene glycol, polypropylene glycol, polyethylene glycol copolymer. And this is used in the presence of water for the exfoliation of graphite. The resultant is high yield and the production of a less defective, perfectly sp2 carbon containing graphene sheets. And these graphene can be functionalized to form nanocomposites, and that can be used for variety of applications, including catalysis. And these graphene-based nanocomposites are already used for hydrogenation reactions, hydrolysis of reactions, coupling reactions, oxidation reactions, reduction reactions, etc. So as to improve the application of graphene in catalysis, here we introduce the metal oxide ceria to graphene, because ceria has a redox nature, and it can be well used in both reduction reactions as well as in oxidation reaction, because it can act as a buffer for oxygen. And ceria nanocatalysts are widely used for a variety of oxidation reactions, and our interest is on cyclohexene oxidation because the products are valuable, and if we are using hydrogen peroxide as the oxidizing agent, the byproduct is only water. And the products are cyclohexene epoxide, diol, cyclohexenol, etc. And here we prefer the synthesis of cyclohexene epoxide. So the major objectives are preparation of graphene sheets in a green environment, insertion of ceria to graphene for the development of a better catalyst, characterization of graphene-based nanocomposites, and also cyclohexene oxidation using hydrogen peroxide as the oxidant. About the experimental for the preparation of the nanocomposite, the graphite is sonicated in aqueous medium, and we are using, as already mentioned, P123 as the surfactant for the exfoliation. And after 3 hours sonication, the unexfoliated graphite is separated, and then cerium nitrate is introduced, and for the hydrolysis, sodium hydroxide is also used. Then hydrothermally treated for the composite formation, and after calcination, we are getting CeO2 incorporated graphene. Next is the catalytic reaction. Here, the solvent used is a green solvent, acetonitrile, and the oxidant is hydrogen peroxide, as already mentioned, and we started the synthesis of cyclohexene epoxide. And about the material characterization, this is the X-ray diffraction pattern of ceria graphene, and it indicates the presence of or the formation of a fluoride structure of ceria over graphene sheets. And the FTIR analysis indicates aromatic CZ, carbon-carbon double bond vibration, and also the fluoride ceria vibration at 460 centimeter raised to -1. And from the TEM analysis, we can see the sheets of graphene and also the well-distributed ceria particles on the graphene sheets. And the fluoride ceria lattice fringe at around 0.32 nanometer, corresponding to the 111 plane of ceria, is also visible from the TEM images. Next, we go to the cyclohexene oxidation reaction. We tried the reaction with the pure ceria as well as ceria incorporated graphene. We cannot use graphene for the reaction because the graphene dissipation remains in a homogeneous mixture even after hydrothermal treatment. So we cannot recover it. We cannot use it as a heterogeneous catalyst. So we tried the reaction using ceria as well as ceria graphene. And the incorporation of graphene to ceria enhanced the catalytic activity and also the selectivity towards cyclohexene epoxide. The non-catalyzed reaction is not much active. And the reaction conditions are a temperature of 80 degrees Celsius, and the solvent is acetonitrile, and for 3-hour reaction using 10 millimole substrate, and the cyclohexene oxidant to cyclohexene to oxidant molar ratio is 1:5, and the major product is cyclohexene epoxide, and conversion is 69%. So the major conclusions are: here, graphene is used as an effective support for ceria for enhanced catalytic performance, and the catalyst preparation and catalytic reaction is performed under perfectly green conditions, and cyclohexene is effectively oxidized over the graphene nanocomposite, and epoxidation was the major reaction, and the material characterization confirms the formation of fluoride ceria over exfoliated graphene sheets. These are some of the references. I would like to acknowledge my University of Calicut, and the college, SNGS College Patambi. And the lab work is done by a MSc student during her project work. And she would like to acknowledge the research scholars for their support. And SAFE Cochin is acknowledged for the characterization facilities, extending the characterization facilities. Thank you. Thank you all for